Hello, everyone. I'm Lori DeToro, Senior Communications Manager for Turntide Technologies. Thank you for joining us today to learn more about the new Axial Flux Motor Electric Drive Unit. We are thrilled to have VP of Engineering Adam Nixon presenting for us this morning live from our Gateshead manufacturing facility. Before we get started, we have some housekeeping tips to share. This presentation is being recorded and will be available on demand on the Current and Wave website. We will be taking questions at the end of the presentation, so please use the QA section, not the chat section, to ask your questions anytime during the webinar, and we will answer as many as possible at the end. We also have the link for our April webinar in the chat. This webinar will cover different diesel hybrid systems and how axial flux motors are beneficial in them. Go ahead and register for that before you log out of the session. And remember, this is a live event going on in 2 countries for us. So when we mess up, and we probably will, laugh along with us. That's it for housekeeping. We're ready to get started. Adam, take it away.
Welcome. My name's Adam Nixon. I'm the VP of Engineering here at Turntide. I'm joining you here today for this webinar on the electric drive unit advantages and tech tour related to Turntide's new product. Next slide, please. So starting with market trends, the electric drive units have been around for a few years with great exploitation in the passenger car market. So what we see from that market is that it's typically a high volume bespoke solution that's utilized per platform with high integration of multiple components in a platform that's suitable for one specific product variant or application. In the commercial vehicle market, we see mid-volume solutions adopting across platforms, typically limited to a 3-in-1 integration with an e-axle solution. What we're seeing is in the off-highway construction and agriculture and recreational market applications, which are typically moderate volume but high mix platforms, there's a real demand, not just for off-the-shelf solutions, but solutions that do not require long development cycles with flexibility and a modular approach. So with our solution, we see we can address the challenges of space constraints, which are extremely challenging, requirements for high efficiency and high performance. And this has really driven the demand and the development of our product, which we've now released, which is an axial flux-based electric drive unit. So in summary, Turntide are providing an axial flux electric drive unit, total e-powertrain solution under one roof with no extra efforts for sourcing, integration, and commissioning of the individual components. Next slide, please. So covering the market size and growth outlook that has led to us developing this program and product, axial flux motor technology is known for its high torque density, compact form factor, and reduced mass. And it continues to accelerate its penetration into EDUs, electric vehicles, hybrids, and off-highway applications. In terms of the global axial flux motor market growth, the global market has reached $3.16 billion in 2026 and is expected to hit up to $8.82 billion by 2035. In terms of the relevance to the EDU market, automotive use accounts for 41.6% of the demand, confirming the EDU segment as the largest driver. More than 65% of electric vehicle manufacturers are exploring axial flux motor adoption, and over 61% of US EV prototypes now include axial flux configurations. In summary, axial flux-based EDUs are transitioning from niche to mainstream in high-performance, lightweight EV architectures. So firstly, covering 2 of the products that make its way into this combined and integrated electric drive unit. Firstly, the motor technology. So we've recently spoke about in recent webinars and press releases about our new product platform of axial flux motors. So there's several sizes and variants within this. Firstly, there's 3 main diameters that have currently been released, which is the AF300S, AF400S, and AF430S. And these products are stackable. So in its single stack configuration, this is what we refer to as the S. And in the double stack configuration, this is what we refer to as the D series. And you can see from the table there that these cover a range of applications and performance targets. So firstly, in the smaller diameter with the 300, we have a maximum speed of 8,000 RPM. And a continuous maximum power of 73 kilowatts, up to the larger size, which runs up to 3,700 in the 430S, with a continuous maximum power of 101 kilowatts. Next slide, please. And secondly, from the inverter technology, What we're showing here is what we refer to as our Generation 6 size 9 inverter. This is a product that we've recently released into the market. So our high voltage inverters are designed for electric vehicles, also being suitable for traction applications, pumps, and auxiliary loads, with advanced functional safety features within there. Looking at the specifications there, these are rated for a nominal VDC of 350 volts, a boost current of 540 amps RMS, and a continuous current of 200 amps RMS. These are liquid-cooled inverters, and from a functional safety perspective, are compliant to ISO 26262 with an ASIL C rating. And in terms of the relevant features and functions to this application with the EDU, they have some really critical traction application features which have been integrated into software, which make them perfect for this application. So this covers the advanced control features that I just referenced that make them the ideal subcomponent for the EDU. So we have a feature within our Gen 6 software that we call user code, which allows development of custom user code to integrate within the vehicle architecture and the development by the customer of their own bespoke features to be able to deal with the specific implementation of the vehicle. Looking at from a motor control perspective, the Gen 6 architecture has the ability to deal with a number of different motor technologies. And within the torque modulation feature, we're able to bring together a lot of kind of essential motor control features required by the applications into one unified integrated controller: motor speed, torque control, temperature management. And in terms of advanced features that are suitable for implementation in this EDU, we have enhanced traction control features through the physics-based vehicle models that we have implemented. So that allows control to eliminate jerks and clunks that can be seen in torque demand generation, including in applications such as hill hold and with also robust stall detection. Next slide. So then moving on to the EDU. So what we're showing here on the bottom right and what we have here in person is one of the examples of the different products that are possible within our EDU range. So this is based on the AF400S that I mentioned before, with a nominal 400 mil diameter and a 5,000 RPM maximum continuous speed, and also with the Gen 6 size 9 that I just covered there. But the overall architecture allows a modular architecture. So as I mentioned, there are the options for different motor sizes, and that allows multiple configurations related to the specific application. There's high torque density that's delivered by the motor that's at the heart of this. So we have 53% higher torque density than competitor motor solutions and as an EDU, and 56% less size and weight compared to EDUs that utilize competitor radial flux motor technology. We have a simplified gearing design utilized within this. So we have a single stage gearing here, which reduces the complexity and also reduces the size, and also improves the reliability of the overall unit. Because we're also using the Axial Flux motor technology, which delivers its rated power at a lower speed range, that means that we don't need the high gear ratios that are seen in competitor radial flux solutions. Shared cooling system. So as we'll see when we go around the walk around of the product, we have integrated cooling between the motor and the inverter, which simplifies the system integration effort. And from a serviceability perspective, going back to what we talked about from the market size, we've seen to now on the market heavily and highly integrated solutions that pose real challenges in terms of serviceability and maintenance, because our EDU is based on individual components that are validated and they've been integrated together in such a way that they can be separated and serviced or replaced in the event. In terms of other benefits from a performance perspective, as we mentioned, the utilization of the pancake motor geometry and the short axial length really reduces the overall size and eases the integration within the vehicle architecture. The inverter software features that I mentioned before are taken through from the inverter to the EDU level. From a certification perspective, there's the 26262 that I mentioned, and EMC compliance to Reg 10, and overall high environmental specifications based on ISO 16750. So both the motor, the inverter, the gearbox, and the overall unit are designed for rugged applications. From a system level, because of this modular-based approach, it means that it's really plug and play. The individual components are tried and tested, and that gives confidence to the customers and integrators who are going to be using this technology and are often very familiar with the individual components already. The motor and the inverter are already prepared and characterized, and that's the benefit in Turntide providing the overall system solution rather than individual components, is that we've developed and went through the characterization pairing activity on our dyno facilities. So there's no step required there when the customer buys the overall solution. There's no requirement for oil cooling, as the gearbox is self-contained and doesn't require an oil cooling system, which simplifies the integration effort. There's flexibility in terms of the inverter mounting. So as you can see on the slides there, we're showing a configuration where the inverter has been mounted onto the solution, and it comes as one full package. As we're showing here in person, you'll see in the walkthrough, there is the ability, because it's not one kind of tooled integrated enclosure, and there are individual separate products that have been mounted together, to be able to locate the inverter in separate locations, which we've seen from initial applications that we've been working on is a very real benefit that allows the inverter to be placed closer potentially to the VCU and in locations that can protect it. And then in terms of configuration that we'll talk about in following slides, we have the ability within this package to change the differential slip configurations to limited slip, to an E-locker or other options. And within the motor product, we have the ability to change the winding turns, which is the to do with the winding configuration, which means we can optimize the performance map and the voltage and current trade-off for specific operating points. So what we're showing here is a representation of one of the SKUs. So on the right-hand side, we can see some performance curves which are based on the AF300D base EDU, utilizing 3-turn windings at 360 volts. So in the blue line there, we can see the peak torque capability based on 20 seconds duration. So we're seeing over 4,000 Newton meters of real torque there. And the continuous torque, the torque that can be delivered continuously with no temperature derating, we're seeing close to 2,000 Newton meters of combined wheel torque. And obviously that performance and that specific graph depends on the specific turns, motor configuration, and gear ratios. But again, that gives flexibility to optimize those different configurable parameters for the specific vehicle speed, the specific torque requirements, and also the specific battery pack that's being utilized and the related voltage. So covering back again about the configuration and what that means and how that all comes together. So in summary, we have the ability to change the ratio within the gearbox. We're able to change the motor turns within the windings, which is a standard core offering from a motor to optimize for the voltage and performance map. We have the ability through the design of our AF motor topology to be able to stack to a single and double, to be able to multiply the torque and power delivery. We have a range of different motor diameters within the product family to be able to, again, look at the balance of torque versus speed and power, weight, and size for the specific application. The ability within the motor design to be able to reorientate the motor. So the motor has the ability to be able to be clocked at 90-degree orientations. Inverter location, which I've just covered. There's some flexibility there in terms of the distance and relative location that can be located. And then, as mentioned, the differential slip options between looking at a limited slip or E-locker, all within the package with no change to the externals. So how that comes together in terms of what we see from the Axial Flux EDU, we see high performance. So utilizing the Axial Flux technology leads to an overall EDU with unmatched power density to traditional radio flux topology. In terms of space constraint, the reduced axial length of the motor and the simplified gearing and the delivery of the performance of the nominal power at a lower speed reduces the complexity of the gearing and the overall package. In terms of efficiency and the impact on range, the reduced weight and the high efficiency of the subcomponents and the overall EDU can lead to extended battery life. And the modular design, the configurations that I just covered on the last slide, allow real kind of tailoring of this solution to the specific application. In terms of maturity, the individual components as covered are off-the-shelf and in-production products. So they've been individually tested and validated. What we're showing in the bottom left there is this product and its various iterations as we went through the development. I've went through testing at the Axial dyno test facilities. We've got a program of system environmental validation to again ensure compliance to the usual standards of environmental requirements, ISO 16750. And we are currently underway with mule testing in customer vehicle applications to really test out the performance, gather data in the field, and undergo final validation of this product as it enters the market. So in terms of the competitive position, what we're looking to show here, there's a lot of information on the slide, of course, is how the axial flux motor technology that we offer and then the resultant electric drive units compare against the competition. So in the bottom left, we can see that our axial flux motor here, the F300S, has a higher peak power than competitor solutions. And when that translates into the electric drive unit, when you're looking at the peak power and the associated weight of the gearbox, motor, and inverter, we see that we have a lower weight solution with a higher power delivery, peak power delivery. So when you look at the metric of kilowatts per kilogram, which brings those two metrics together, we are at least 49% higher than the competition, and up to 68% in some cases. So in summary, we have superior performance, higher peak power, we have a lighter construction, smaller package, we have a secure, power-dense optimized inverter, a low-cost simplified gearbox, and we've optimized the overall subcomponents and overall package for powertrain efficiency. So now we'll engage in a product walk around. So starting on this side, as mentioned before, this is showing the configuration where the inverter is separate to the motor. So they're only attached by the high voltage power cables and the three-phase high voltage cables here, as well as the cooling hose. So if we look around on this side here, you can see that typically we would advise that the inlet for the cooling goes to the inverter first, as that's the most temperature sensitive. And then effectively it loops through the inverter in series through this hose into the motor, and then back out on this following hose here. So the same as any other component integration, you would have one inlet and one outlet, reducing complexity for any kind of system integrator or customer. In terms of the cable connections, both on the inverter and the motor, we have the utilization of high voltage glands, which are IP67 and IP69K rated, again ensuring the robustness and durability of this product in the application. As we come around to the other side, we can see that the gearbox and the motor are integrated here and bolted together with this flange. But because of the orientation of the bolts, this allows basically reclocking of the motor to different positions. And this can be particularly useful depending on the vehicle system design and where the relative battery location is, but also where there may be any constraints from the overall structure of the car, which could lead to the need to reorientate. We've shown here just effectively blanked connections. Typically you would have the CV joined cup here for connection. So we've just showed a blank representation of that. And internal, within between these two outputs, is where we would have either the limited slip differential or the e-locker. Okay, so the latest question was, when will first prototypes be available to customers? So we're now actively engaging with customers and delivering samples. So as mentioned earlier in the presentation, we are already engaged with several first adopter customers undergoing vehicle testing as we speak. So I really implore people to engage with the sales team, with the applications team about your application. We're in a position now to be able to deliver samples for use cases.